Hello everyone again. This is lecture 9 part 2 of wave optics. In the previous lecture we started with one of the forms in which polarization is happening in our natural surroundings, that is by polarization by scattering. Today we will go on with further discussions and we will go with what happens why polarization is done by reflection. What is this instance? In the previous lecture I already explained to you what is polarization, what is the device used for polarization and so on. So let us not waste any time, let us move on with the further discussions only. So I am Sameer Lavankar, let us begin our discussion. So right now we are in the last stage of wave optics, that is polarization. Before that we understood every concept, so we started with the wave optics definition. In Hume's principle we understood the concept of wavefront and how can we find the wavefront at some time t is equal to tau, given that we have the wavefront at some time t is equal to 0. Then the refraction and the reflection laws were being proved using Hume's principle and wavefront concept. Then in coherent and incoherent addition of waves we understood the concept of intensity being maximum or minimum based on coherence and incoherence. Also we understood a small concept of Doppler effect in this. In the interference of light wave and Young's experiment, a beautiful experiment by Young's was being done, that was double slit and single slit experiment, and the bright fringes and dark fringes were being observed based on the path differences. So destructive interference, constructive interference, etc. were being explained in this concept. Finally in the diffraction concept we understood the bending of light which is occurring due to the obstacle being of the order same as the wavelength. Then the single slit diffraction pattern was being observed, the mechanism, the procedure of single slit diffraction pattern was being explained to you. Then double slit also was being explained, it is nothing but a superposition of two different diffraction patterns. And finally we are in polarization. In the last lecture I explained to you one of the method of polarization, that is the method of scattering or polarization by scattering. Today we will go on with further discussions of polarization by reflection. Okay. So please look over here carefully. So polarization by reflection. So this is another method of by which polarization is being done. Just to reiterate to you, what is polarization? Polarization is nothing but the process of conversion of an unpolarized light into a polarized light. How it is being done? A device is being used called as a Polaroid. Polaroid is nothing but a sheet kind of structure such that when the light is being passed through it, the electrons, let us suppose it is a y-axis Polaroid, then only and only the the molecules which are passing or which are displaced, which are being displaced in y direction will not be observed, except them all the molecules will be observed. Hence an unpolarized light will convert into a polarized wave, or let us suppose a y polarized wave. So this is the complete process. The process of conversion of unpolarized light into polarized light is called as polarization, and the device being used is called as a Polaroid. So one of the method again, so first was the scattering. Let us move on to the second concept now, that is polarization by reflection. So in figure B shows light reflected from a transparent medium, say water. So let us suppose that a reflection is being happened here, or let us suppose some refraction is being happened here. From the figure, as you can see, it is quite evident there is a mixture of both reflection also and refraction also. So sometimes, or in real life scenario, every time complete any subject or any surface is not 100% reflective surface, and nothing is 100% refractive surface. It is always a combination of both. But for considering or for understanding some concept, we understand that if the light is being incident on a surface and we are assuming it to be an ideal nature, it may get reflected. And similarly for different cases, we want to understand the concept of refraction, we understand it as an ideal surface, and hence every light which is incident gets refracted. So now we are assuming some of the real life application, and we are assuming that if the light is being incident, then it is reflected also and refracted also. So now first of all let me explain to you from here only. So first of all let us please look over here carefully. Incident light has a unpolarized wave. So as you can see, let me magnify the wave for you. So it is the direction, so it is the displacement is being happening in this direction also, and there is a dot also. That means the displacement is happening inside the plane also. There is a displacement like this, and there is a displacement like this, and the propagation of light is in this direction. If I explain to you like this, so let us suppose that this is the surface, this is the direction of wave. If this is the direction of wave, then there is a displacement happening in this direction, and there is a displacement happening in this direction. So similarly the waves emanate and this touch the surface at this point. Let us suppose this is the point I am telling you about. So this is the complete thing which I need to convey. Moreover, as you can see here, on the reflected side you can see only one form of, only dots are being observed. That means some sort of polarization has happened of these part of molecules when it is reflected from the surface. But when you try to see it for the refracted side, Now try to see this for refracted side, then you can see that there is no polarization being happening. As you can see, the form is similar to that case of incident wave only. So these are some of the instances which we observe from this figure. Now let me try to explain you everything which is written on the left hand side. Okay. So figure B shows light reflected from a transparent medium, say water. So as you can quite evident, this is air, this is water for you. So figure B shows light reflected from a transparent medium, say water. As before, the dots and arrow indicate the both polarizations are present in the incident and the refracted wave. So this concept I already explained to you. We have drawn a situation in which the reflected waves travel at right angles to the refracted waves. So we have assumed an angle of incidence, such that the reflected waves travel at right angles to the refracted wave. That means this angle is 90 degrees. As you can see, again we have drawn a situation in which the reflected wave, so this is a reflected wave, travels at right angles to refracted wave, that means this angle is given to you as 90 degrees. So just for your information, let me write this as right angle. Okay. The oscillating electrons in the water produce a reflected wave, quite evident. Oscillating electrons produce a reflected wave, as the concept we already understood in Newton's principle. Only and only we are assuming they as wavelets as an apolarized light here. So that is only the difference, rest all the concepts are same. So the oscillating electrons in the water produce a reflected wave. These move in the two directions, transfers to the radiation from wave in the medium, that is a refracted wave. So what does it try to say is that the oscillating electron produce reflected waves. So the electrons are being absorbed. The electrons at this point, what they try to do is they go in this direction. So what does it happen? The oscillating electrons in the water produce a reflected wave. So electrons are present here. So due to that, reflected wave has been observed. So reflected wave has been observed, and similarly these move in the two directions, transfers to the radiation from wave in the medium, that is refracted wave. So what does it happen? Because of oscillation, the movement of wave has happened in two directions. One was a reflected wave, one was a refracted wave. Okay. The arrows are parallel to the direction of reflected wave, quite evident, the arrows are parallel to the direction of reflected wave. Motion in this direction does not contribute to reflected wave. So anything which is happening in reflected wave or refracted wave won't happen in the other case. If it is happening in reflected wave, it won't happen in refracted wave, and if it is happening in refracted wave, it won't happen in reflected wave. So as the figure shows, the reflected light is therefore linearly polarized perpendicular to the plane of the figure represented by dots. So quite evident, as I already explained to you, because the concept which is happening here is not happening here, it is being absorbed. That is why the reflected light does not have this if I explain to you, let us suppose this is the what we can say interface, and this is that plane of polarized light being explained here. So because this thing is being absorbed by the refracted part can't take it into picture. So everything is being absorbed for reflected, and hence this can't be visible. You can't see this thing, only the polarization or the polarized wave which is happening in this direction was being put apart in this reflected portion. Why? Because of oscillation of electrons. So as the figure shows, the reflected light is therefore linearly polarized, quite evident it is linearly polarized. What is the meaning of linear polarization? If the displacements are happening in a linear sense, the displacement is happening in linear sense, if let us say this is the direction of propagation and the polarization or the points of the locus of points are in this way, if we see it from above or below, it can be observed as a linear line, that is why it is called as a linearly polarized wave. So as the figure shows, the reflected light is therefore linearly polarized perpendicular to the plane of the figure, quite evident it is perpendicular to the plane of the figure. So if this is the figure, then it is going inside, hence it is perpendicular to the plane of the figure. This can be checked by looking at the reflected light through an analyzer. So this is just the method, how can we observe that if it is achieved or not. Okay. So this thing is being concluded, this thing is being explained. Okay, now please look over carefully, because one of the thing called as Brewster angle will come into picture. What is this angle? Please let me explain to you. Okay. So the transmitted intensity will be 0 when the axis of the analyzer is in the plane of the figure, that is the plane of incidence. So which analyzer is being talked about here? If we want to check that the linear polarization has happened or not, where the linear polarization will get happen, it will only and only happen in reflected wave. How will we check it? We will check it by looking at the reflected light through an analyzer. So maybe an analyzer can be kept here and it can be checked if the polarization or the polarized wave which is passing through an analyzer is only of one single sense, if it is a transverse wave or linear transverse wave or not. So, that can be checked directly. Now, the transmitted intensity will be 0 when the axis of the analyzer is in the plane of the figure. So, it is just making an angle of 90 degree. If the angle is 90 degree, we know that it is I naught cos square theta 90. If cos 90, hence it will be 0. So, that only explanation is being kept here, nothing else. That is the polarization is being done like this, the angle is being kept like this. If the angle is being kept like this, hence the intensity will be 0. Only that concept is being explained here. Now, when unpolarized light is incident on the boundary between two transparent media, the reflected light is polarized with its electric vector perpendicular to the plane of incidence when the refracted and reflected waves make a right angle with each other. So, this is only and only explanation of what is happening in this figure. So, they are just trying to explain is, let us suppose this is an unpolarized light. Let me write the unpolarized light as UP. Let me write this as UP. Then it is saying that a polarization of the reflected light will occur as long as the angle between the reflected wave and the refracted wave is 90 degree. So, this is just the explanation which is being explained in that line. I will just repeat it again. If this is the unpolarized light, then this will be a polarized light. So, this is just the explanation which is kept in second point here. Okay. Thus, we have seen that when reflected wave is perpendicular to the refracted wave, the reflected wave is a totally polarized wave. Quite evident that we have seen that when reflected wave is perpendicular to refracted wave, this scenario only, the reflected wave is a totally polarized wave. What is the meaning of totally polarized wave? That a polarization has happened and all the molecules, all the electron molecules are being absorbed except one polarization or one direction of polarization, except that. So, this is again the just a summary of this part only, second point only. So, the angle of incidence in this case is called as Brewster's angle. So, this if I write this as I B, or if I for now I write it as I, let the angle of incidence be I here. So, the angle of incidence in this case is called as Brewster's angle. Please remember this because this can be very important for your examination point of view, and is denoted by IB. So, let us I am writing that I is equal to IB. When it is like this, if I let us say write this as A, this point as O, this point as B. So, when angle of A O B is equal to 90 degrees, then angle I is equal to IB. What is IB? IB is called as Brewster's angle. I is equal to IB, IB is called as Brewster's angle and is denoted by IB. So, we can see that IB is related to the refractive index of the denser medium. Quite evident, as we know that there are diffractive indices different for different cases, and hence we will get different refractive indices. So, we can see that IB is related to refractive index of the denser medium, since we have IB plus R is equal to pi by 2. So, IB plus R is equal to pi by 2, quite evident, because if this is 90 degrees and if I write this as value of R, then by mathematical formulation we can get that this angle plus this angle is also equal to pi by 2. Therefore, from Snell's law, so Snell's law states that mu is equal to nothing but sine of IB by sine R. These all concepts were being explained to you when we proved the reflection laws using the Huon's principle. So, you can just refer to previous lectures and you will find these concepts there. So, just now nothing else, we are just writing sine IB as sine IB only, but using these equations we can get R is equal to pi by 2 minus IB. So, sine pi by 2 minus IB, as we know from mathematical trigonometric calculations that sine pi by 2 minus 90, sine pi by 2 minus A is equal to cos, hence this will be equal to cos of IB, which is equal to tan of IB. So, refractive index is nothing but equal to tan of IB, where IB is Brewster's angle. So, maybe in the question, maybe in the exam, Brewster's angle will be given to you and you will the question would be asked, please calculate the refractive index. So, it is nothing but you just need to find the tangent of that. So, it is nothing but tan of IB. So, this is known as Brewster's law. So, please remember this is Brewster's law. What is Brewster's law? Brewster's law refers or states that if the angle of incidence is IB, then the refracted line will be linearly polarized only and only when the angle between the reflected light and refracted light is 90 degrees. So, this is the complete explanation of Brewster's law for you. Okay. So, now let us move on to more explanation about this. So, for simplicity we have discussed scattering of light by 90 degrees and reflection at the Brewster's angle. So, this is just the explanation of previous part, and reflection is being done and Brewster's angle is being achieved. Please make sure Brewster angle is only and only visible or applicable when the angle between the reflected and refracted light is 90 degrees. So, in this special situation, one of the two perpendicular components of electric field is 0, quite evident because the polarization has happened, the electric field component in one of them will be 0. At other angles both components are present, but one is shorter than the other. So, this is the theoretical part again. So, there is no stable phase relationship between the two perpendicular components, since these are derived from two perpendicular components of an unpolarized beam. So, because displacements can be different, because it depends on y is equal to sin kx minus omega t and can be different for different cases, sometimes the value of k may differ and hence the value of displacement in both these directions can also differ. So, when such light is viewed through a rotating analyzer, one sees a maximum and a minimum of intensity, but not complete darkness. So, because the intensities can differ, why it can differ? Because the value of polarization, because the unpolarized light in let us say y phase and z phase may differ. So, because the displacement can be different, hence the intensity can be different. Because they are not of the same phase, hence the value can't be 0, because the diffraction or interference, destructive interference won't occur, and therefore we can't see complete darkness. Only an intensity can be minimum, so that some light will be visible, and at some point a major brightness can be visible. So, this is only been explained here. Why it is happening? Because there is no stable phase relationship. And why there is no stable phase relationship? Since these are derived from two perpendicular components of an unpolarized light. So, when the perpendicular components are being done, when cos theta or sin theta angle is being put, because it is a mixture, I already explained to you that an unpolarized light is basically a mixture of all. So, sometime what will happen is that the sin component can be greater or the cos component can be greater. So, hence the addition in both these can be different, hence the value of y polarized wave and z polarized wave will differ. So, because it is differing, hence the intensity will also differ, and hence because the intensity will differ, the case may be that we can't see complete darkness. So, this is just a theory part only, no need to go into deep explanation by this. So, different concept was being observed that this kind of light is always partially polarized. Why it is partially polarized? Because the components are differing, that is there is no phase relationship. So, this can be asked as a theory part only, why it is always partially polarized. So, you can just explain that because the components of light are being different in y polarization and y polarized and z polarized, and therefore, there is no static phase relationship, and hence the intensity is only minimum and maximum, it is never 0, that is I min is never 0. So, this kind of light is called as partially polarized wave. Okay, so, now this is the final conclusion of polarization by reflection, and that will be the end of our wave optics. Okay. So, polarization by reflection: when an unpolarized beam of light is incident at the Brewster's angle on an interface of two media, only part of light with electric field perpendicular to the plane of incidence will be reflected. So, quite evident. So, just let me explain to you again with a diagram also. So, it is saying that only and only, so this is one of the part of what we can say unpolarized light. So, only that will be reflected which is perpendicular, only that part of light with electric field vector perpendicular to the plane of incidence. What is the plane of incidence? This is the plane of incidence for us. So, only part of light with electric field vector perpendicular. So, as you can see that this is perpendicular to this direction, hence if this is the z, if this is the let us say one plane, this is another plane, quite evident that these are at 90 degrees to each other, even if I rotate it in this form. So, because that electric field vector has the displacement in perpendicular direction to the plane of incidence, only and only then the polarization has occurred. So, this is again one of the way in which the Brewster's angle is being achieved. This is nothing but it is just a theoretical part of how the mathematical formulation is being converted into some theory. Now, by using a good polarizer, if we completely remove all the light with its electric vector perpendicular to the plane of incidence and let this light be incident on the surface at the prism at Brewster's angle, you will then observe no reflection and there will be total transmission of light. So, this is again one of the application of Brewster's angle. It just says that if we take that source of light and we pass through a prism, then what will happen is you will see no reflection. What does it mean by reflection? There will be no reflection, there will be complete transmission. This is only the explanation. This is all. So, just please I will not go into much detail. I will just explain it again. So, what is happening is, if we try to take the Brewster's angle into picture, if that angle of incidence is such that the angle between the reflected and the refracted is 90 degrees, only and only then Brewster's angle is being formed. And if the Brewster's angle is being formed, then if we take the reflected light, and we pass through it a prism, then what will happen is there is no reflection being observed. So, there may be no light which will pass in this form, and there will be total transmission of light. So, complete light is being went inside the prism. So, this is just the explanation of Brewster's angle. So, let me stop it here only. This is the final conclusion of your wave optics. So, complete polarization is also being explained to you. In the next lecture, I will just summarize the complete wave optics, so that every concept is being intact upon, and I will explain just how the complete procedure was being explained, and that is the complete end of your wave optics. So, let me stop it here only. Thank you.